So now the code seems to be at least not having errors. So in order to check the outputs, we can do some prints. So let's see, like we are going to print here the table that contains C. It's just to check how we see on each iteration. So here we're passing K. So we're gonna check CK, and then we can use our print table function, right? Passing CK, and we need to pass the support, remember? So we can build the support on the fly with our function count occurrences of I and the transactions, and we are looping. I mean, basically here I'm counting the occurrences of each item set. So I need to pass the item set and the list of transactions for IT in CK. So I'm looping over the item sets. Let's check if this works. Okay, at least it's printing C. So we need to do something similar with L. So we can, every time we update L, which is here, so we can print L every time is updating with something that is not empty. So we can copy this. Table for L, and we can again use our function to print the table for LK and the supports that we have in this dictionary. Okay, so let's see. Here we go. So in this example, this is actually the same data we used for the example in the previous video. So we can see here that it's printing C2. We already print C1 right before. So C2 seems to be fine. Then L2 is just the frequent ones. It's discarding the ones with less than 2 transactions. Then C3 is all the candidates of size 3. Seems they are fine. And then L3 are just the frequent ones. And finally, there is one candidate of size 4, which has like a count of 1, and that is the end of the algorithm because L4 is empty, right? Cool. So now we just need to implement the code that produces the rules according to the frequent item sets found here. Now we're going to generate the association rules. Remember that we need to loop over all the frequent item sets, in other words, the item sets in L, and then for each of the item sets we need to generate all the combinations, and then producing all the rules according to the combinations, and producing all the rules according to the combinations, and then calculate the confidence, the lift, and the support. Okay, so let's do that. We need to loop over L. Frequent item sets of size 1 cannot produce significant rules, right? So we can start from the frequent item sets of size 2. Remember that is in K equal to 1 in the dictionary that contains L. And then so as soon as we are inside the item sets of size, in this case I, we need to loop over the item sets there, right? So in this case it's Li. So now we are okay, we are standing in one specific item set, so we need to produce S. Here we are going to need a helper function. Let's say let it call power set, with basically all the combinations that can be produced from L, in this case Ij. This is our item set, right? This function is probably going to need this represented as a set, so we're going to implement this later. The way the power set functions usually are implemented, return all the subsets, and usually the last one corresponded to the subset that contains all the items. And in this case, it's not necessary, right? So we can pop S, and then we're going to get rid of the last element, which is the subset that contains all the items. And then we can go over each element in the subset and generate the rules. Remember, that's what was first S. We need S, which is a set of Z. We need X, which is the set of produced by the item set. And then we need XS, which is the set of the difference. So we need to make sure that the rule S arrow X minus S, right, as we saw in the previous video, satisfy the support and confidence condition, right? So the support of X, for this we can use our helper function that counts the occurrences of X in the transactions. We can also use our helper function for the support of X minus S, let's call it like that. Okay, so now we can calculate the confidence. The confidence, remember, that is the support of the item set divided by the occurrences of, in this case, S. And the lift, remember, that is the confidence we just calculated divided by this support divided by the number of transactions, which is basically the length of the transactions, right? If I'm not wrong, we calculated above. So in cases the confidence is greater or equal than the mean confidence, not sure if we have this threshold defined, but we're gonna do it soon, and the support is greater or equal than the minimum support, then it means that the rule is and that we have an actually interesting association rule. We can actually basically use a string to print out all the rules that is going to be accumulated here. Let's assume we're going to have a helper function that will make sure, or will take care of printing the association rule related to x minus s and s with the previously calculated confidence, support, lift. It's going to need the number of transactions. That's it. We're going to have to initialize this variable with an empty string. Okay, so let's implement our needed helper functions. So the first one was the power set, right? It's basically all the subsets. There's a bunch of ways to implement this, but we're going to use one provided by the itertools library. So we are going to use combinations. It's basically a function that returns all the possible combinations of a specific size, and the function chain that is going to put all the iterables returned by combinations in just one iterable, right? So let's say that it's kind of sounds complicated at the beginning, but it's not so hard to understand as soon as we type it. So the first thing is we need to create all the combinations. It's going to be of S on size R, right? For R in the range, and here we are going to create all the possible sizes. We don't want size 0 because it's the empty set, so we can start from 1, and then it's going to go up to the size of S. Let's say S is the item set, plus 1, and so here we have all the combinations, but they are a bunch of iterables, so we need to put them together in just one iterable. For that, we're going to use the function chain.from iterable, and then we want this as list, so we can actually take care of this here, and we can delete this there. That's fine, hopefully. And then let's check it. I mean, okay, that's a good point. We forgot to define S. This is not so smart, right? Let's do it like that. Okay, but that passed. I mean, now we need to just make sure that we have the number of transactions and later the function write rules. So let's implement now the other function, the other helper function called write rules. That this function, recall, that is just in charge of printing out the rules, so we can use the name of the variables we've been defining all the time, x, let's say minus s, right, and s. This variable is representing x minus s. The confidence, the support, the lift, and the number of transactions. So this function basically needs to return a string. We can call it out rules, that will start as an empty string, and then we can go and add each piece we're gonna need to build the final string. So first, let's print the frequent item sets. In particular, remember that each rule comes out of a specific item set. So let's start by printing that item set in particular, right? So it's going to start from X. This is the main item set we are printing. Then we need to add each specific rule. So let's go first with the rule we're going to use this type of printing, right? S and X minus S, we're gonna need them as lists. Okay, then, so here we are printing basically the same rule S arrow X minus S, that we have them from the parameters, and then we need to just print the indicators. So we can start with the confidence. We're going to use a specific format. If you're not familiar with the string formatting, I encourage you to read online. Now, same way, we just will print the support, which is mostly the same thing here. It's the same formatting, but we can use that, and finally the lift, which is like this, very similar to this, right? And we just return the string. Okay, seems that is fine. Not really. Sorry. Okay, we're supposed to have somewhere the number of transactions. We needed also the mean confidence. Let's choose, I don't know, like 30%, and we can save the number of transactions. In this variable, right? Okay, here we go. Sorry, it's mean confidence. Let's just mean conf. Maybe I didn't run it. Okay. Okay. So here we should just print out that variable, and we should have all the rules. Okay, here we go. Okay, so it seems that it's working. So that's it. Now we have like one implementation of the vanilla version of the a priori algorithm. Thank you for staying here with me, and see you in the next video.